in the world. Oh, that's so. And now, uh, I'd like to finish this quickly, and I'm going to give a talk in the next slide. I'll switch to other one. I hope you see this slide okay. So I'm going to talk about knowledge between holography and statistical optics. And a little bit strange things. I'm really happy to, unfortunately, physical. I'm now in Tokyo. Nonetheless, a long time ago, I have been visited the Jaipur, a beautiful pink city. I hope that it was when I was still young at my first visit. It is kind of my conference in IIT Delhi, and we went to Golden Triangle, and it gives me opportunity visiting Jaipur as well. Okay, today I'm going to talk about little bit strange the things, but what is the talk is all about. And I think the most of the audience, my audience, are student, of course, including faculty members, and you are learning or studying optics. When the university curriculum, you learn much about optics. And the lecture often are given on statistical optics or on the holography, but in most of the case, they are in a separate subject. So in the field of optics, statistical optics is one subject and holography is another, the other subject. And they have a kind of separation in between. So I would like to get them a bit more closer in such a way that we will have a happy knowledge. And this knowledge is not that easy. We will need someone to make this happen. That is the what I call matchmaker. Analogy, concept of analogy helps these two different fields to be merged together and to give a very happy birth to their children. These are the technique that was born from this happy knowledge. I will also introduce these kind of things. This is the old story all about. Now I would like to start a bit of the introduction because this is a tutorial seminar and I think you're familiar with optics but may not necessarily very much familiar with the statistical optics. So I will start with a bit of introduction, very quick introduction of the statistical optics. And here, every optical field is kind of, they have a of statistical nature. In that, by that means, it fluctuates sometimes. Even a stabilized laser is fluctuating statistical behavior. And you observe optical field at 2 points and let them superpose each other in such a way that they interfere each other. Typical example will be the Young's interferometer, which you are familiar with. And now, how Young's the French created is a kind of intensity of this optical superposed optical field. Mathematically, that is something like this. This is a superposed field and takes the complex conjugate to get the intensity. And this bracket means average. Often this average is time average because our eye or image detector cannot follow up the very fast speed of change of the optical field. So it is through that averaging integration, the average is taking place. But average has a very different meaning, so I will touch upon it soon. Anyway, these are intensities of each optical field. And here is a cross term in between that is the kind of cross correlation or auto correlation of this the same field. So this is correlation is what we are interested in. And this term is the what people call coherence function is two different optical fields and their average. And it serves as a measure of statistical similarity between the two fields. So when one field is fluctuating and the other field is fluctuating in completely different manner, there is no correlation in between, then this will be zero, so that you cannot observe any clear Young's fringe. But when it comes to the laser, such kind of fields, they are strongly in harmony with the correlation, then this correlation is very high, so that you will see very visible high quality fringes as a Young's interferometer. So this is the what we call statistical correlation function. And I talked about the averaging. The average was time average, but the mathematical concept in the statistical optics, one concept of the important is ensemble average. What does it mean? Just think of this kind of die. You slow, it has a phase from starting to 1 to 6, and when you slow, the probability of each one phase appears is 1 over 6. So the ensemble average phase number is the probability weighted sum will turn out to be 3.5. That is the average number you find. And actually, in what we are doing is kind of experiment. So we will see the die will come out with the various kind of numbers. So you make the average by taking the summing up all and then divide by the number of your experiment. It turns out in this case 3.2 and 2. They are generally different. But when you continue this experiment infinite time, so you will have a long time of experience, then eventually this time average meets this ensemble average. In that case, we call this process is algorithmic process. So implicitly, we are assuming this kind of assumption, making this assumption. So we believe algorithmic process holds in our experiment. So that is something we assume from the beginning. Now I will explain some of the terminology. The temporal coherence. Temporal coherence is you have already seen two parameters: position parameters, time parameter. The temporal coherence is observation made at the same position, but at the two different times of the optical field, and they are correlated. How they are the waveform or variation is correlated similar at different times. That is the measure of temporal coherence. So when you have the sinusoidal, completely sinusoidal signal with no modulation, they are almost same. So it has a high temporal coherence, monochromatic light. It does. Now, spatial coherence is another concept. Now we will observe at the same instant of time. So time observation time is the same, but the observation location is different at different location. So to feel that different location is the similarity is measured in terms of the spatial coherence. In any way, these two concepts plays an important role. Now, we will let us consider how this kind of coherence function plays an important role. So suppose you have a kind of optical field coming from the light source. They are basically of some statistical nature. So by making use of the interferometer, in the previous example, it was Young's interferometer, and making use of that, we will measure the coherence function. And from that coherence function, it has information about the source. So based on that measurement, we will identify various characteristics of the source. So this kind of way of measurement scheme is a very important role. One example is maybe most of you are familiar with the concept of Fourier transform spectroscopy or simply Fourier spectroscopy. That is, the source has a various spectrum like the line spectrum or continuous spectrum and so broadband source, and light is coming in into the interferometer, microinterferometer, and then you make the difference of the move this arm and take the fringe. This is the correlation time correlation, and this is the coherence function. And when you go to Fourier transform, you will see it's the spectrum. So you can measure the spectrum by making use of the temporal coherence function measuring. This is Fourier spectroscopy. And similar version of the spatial coherence measurement is the very famous experiment of the Michelson stellar interferometer, where you have a 2-point light is getting at two different spatial positions, and they are combined together to make the interference. By moving this position A and B, by moving this distance in between and measuring the fringe contrast, you will get the spatial coherence between A and B. And from Fourier transform, you will be able to get the star's angular size of the star. This is very famous. This kind of the coherence theory is called analytical optics, analytical statistical optics. So then what is other statistical optics? There is another type of statistical optics that is synthetic, what I call synthetic statistical optics. By that I mean we would like to synthesize desired statistical property of the random, the stochastic field or a statistical field. So in such a way that we make the source design, we control the shape and the spectrum of the source. So in such a way that we have a desired random field, it has a desired statistical property. In other words, it is coherence function. So in a sense, it is called coherence synthesis. And when this kind of things become important, is in such typical example. You are familiar with the optical coherence tomography, where you are able to see the inside the fundus of the eye by making use of the temporal coherence. So you make use of the temporal coherence, you will have need desired coherence, temporal coherence for that. So we will be able to control the light source left OCT or such kind of things, one of the example. On the other hand, we will be change the shape of the light source and control the spatial coherence so that we have best resolution in optical lithography and microscopy. So these are very important. How we can control the optical coherence? The basic principle is for the kind of analogy I'm going to talk about. Everybody is, I think, familiar with that optical field obeys wave equation such as this. Oh, I know this. Everybody knows this. And so the light field at one position and two position. So its correlation is a coherence function, as I have described. When I stop the fix one observation position and time and let the other position and time to move or change, then we will continue to make the correlation in between. We get this is ensemble average. You can just think of it. And so because we have fixed one position, one as a reference, so reference is fixed. It does not change with time t1. We will only move time t1 and position r1. In that case, this behaves as if a constant, so it is no surprise that it obeys the same optical wave field. So as a result, we can say two things. The coherence function obeys a pair of wave equation. One position is fixed, parameter is fixed, and for that fixed parameter, the varying parameter, we have a wave equation. So when we switch to other parameter fix, then we will have another set of this field. So this will tells us, what it tells us is the following. The optical field can of coherence function obey the same equation as the optical field. So we have a chance to make use of analogy because we know about this optical field. Many things we are familiar with this, and then we are able to deal with this optical coherence function not in the same way as we deal with the optical wave. So we all hint is available from this analogy. I will explain the next, give one example. So you're a student, so most of you are students, so you are familiar with this kind of problem. In my classroom, for example, in the master course, first year of the master course, I ask one of my students, there is a circular open aperture illuminated by a coherent light, like laser, collimated laser light. What will happen in the far field? Most of the students say, oh yes, I know, I have learned about that. It is in the far field, it is the kind of Fraunhofer diffraction. It is forms like airy disk pattern that looks like this one. Bessel functions, yeah, divided by this one, the zinc function or the zinc function. So, and they know all the resolution and the fast zero comes here. So, okay, you are right. And if I ask the same question to the same student, what happens if instead of the collimated laser beam, if I put a rotating ground glass here, and ground glass is destroying the coherence, do you see something like this kind of diffraction pattern? Students may answer, no, sorry, unfortunately we don't see anything. Everything is averaged out and even the uniform field. So the question is does that mean all the information about this circular aperture making this field is lost? Can we even in that do we have this information about this? Indeed, it has. We have information. So this is called statistical optics. Someone learns about the van Zita-Zernike theorem. The textbook of standard the textbook. This is again Goodman textbook. I translated in Japanese language, and so here you cannot see anything. But if you have a pinhole like Young's interferometer, so you have double pinhole here at this position and the other one here, and observe the Young's fringes and move this one of the distance between two pinhole and observe this the contrast of this Young fringe. You will end up with this contrast really behaves like this way. So you will see these are coherent, although there is no information, looks like no information, but nonetheless through in the coherence function it has. Someone raise a hand. Do I get the answer right now? How should I do that? Okay, then please, after the lecture, I will have a time to answer for that because I don't know how to handle this. Okay, thank you. Thank you for raising the question. Anyway, here we will have that information through the correlation or coherence function. Now, if this is a hologram is illuminated by coherent light, you know that the image is reconstructed. But what happens if the circular aperture is replaced by hologram and incoherent light? Do you see the image reconstructed or not? That kind of issue is the coherence hologram. What is coherence holography? I will explain it a little bit. Okay. Now, I assume you all are familiar with conventional holography. where you have an object, like in this case, letter Fourier is an object, and the reference source point, and have a Fourier hologram, let's just Fourier hologram in this case. You record it, and you have a hologram here, and you reconstruct with a coherent illumination. Then you will have this uh, reconstruct hologram zeroth order plus minus or first order. You will see this image. This is your familiar with this kind of holography. Then again we will come what happens. Instead of illuminating coherent light, if the same hologram is illuminated by the moving ground glass, through the moving ground glass, that means spatially incoherent. Coherence is completely destroyed. Then do we see some image here? Of course not. This is, we see just uniform distribution, but the information is lost or not. As we have seen, the information looks lost, but actually it is not the case. The information will be available after we are getting, if we get the correlation of the field correlation. Field correlation is get detected by making use of the interferometer. The Young's interferometer is easy, okay? But we will have a more sophisticated and more efficient the interferometer for that. And by making use of the coordination, we will be able to get the image reconstructed. This is the coherence hologram. So you may, some of you may be wonder that this is a very big, wide incoherent source. How we can have such high coherence? Usually, the extended incoherent source cannot create the coherent the field. There is even if you have a double pinhole, there is no fringe at all. Why? That kind of big source can create such kind of high contrast coherence. I will explain by using this with simple example of object. Object for just for simple explanation, object is assumed to be just point source, and this is a reference. So this is hologram. The hologram need not be square; it can be any shape or even the 3D surface. Whatever, it's fine. Anyway, you have this is the reference and the object. They are coherent because hologram recording is as much the same as conventional hologram. So they are coherent, and Young's fringe is created. And so when bright fringe is created at the location where the optical path difference is integer multiple of 2 pi or in phase, and dark fringe is out of phase. So these are just the loci or locus of the same the optical path difference. So what happens next? If this hologram, once recorded in this way, is illuminated by incoherent light, what happens? If the light is illuminated by incoherent light, so we will look at take a look at only one possible position. That this is a 1-point source, and it emitted back to the scattered light, scattered back to this location. These 2 positions are in phase. Why it is so? Because this is a light fringe. The light coming here to position coming from here and here are in phase. So from here and here we are sending light back. They are also should be in phase. And from black fringe, dark fringe position, they are out of phase. But fortunately, this out of phase part is blocked because it is dark fringe. It is like a zone plate. You will be able to see the next example that is more familiar to you. And so anyway, then what happens if other position? They are incoherent. We will have another case. Here has another source point. They are emitting light. This point and this point are completely incoherent. Nevertheless, from this position and to this position, these 2 sets of light are in partial, completely in phase. Why? Because this position is located at the bright fringe position. So that means this optical path difference is completely in phase. So source these sources are out of phase, but phase difference is always in phase. So that by creating superposing O, they will create very strongly correlated field. That means two positions become very high coherence, have a high coherence, even though this source is incoherent and extended. This is the concept of coherence holography. I can give you more the easy to understand example. Controlling actual coherence. You have a 2 point, one point source here, and the other point source as a reference. They are on axis. So, they're illuminating light as a spherical wave too, and hologram will be on axis Gabor type hologram, on axis hologram, and it is on plate. And when you read this hologram with the light, you will see the light is reading out with the reference light. Again, you will have a strong point here, and the other one is coming from here, but we just make a focus on this one. This is a very strong focus here. So hologram works as a zone plate. Hologram works as a lens, positive lens here and negative lens. But now here, positive lens, we are looking at positive lens. Of course, you can look at negative lens as well. What happens if we illuminate not the coherent light but incoherent light? So every zone of the bright zone will send the light back to here. And the optical path difference is the integer multiple of lambda wavelengths. In other words, they are in phase. So every point itself are mutually incoherent, but the optical path difference is always in phase. So as a result, 2 point P and R are mutually highly correlated. In other words, it has a very high coherence. By changing this zone plate, you are able to change the two coherence, high coherence position along the axis, optical axis, which kind of application I will explain later. Now, as I said, what we are reconstructing is a coherence function. So to reconstruct coherence, the easiest way is of course the Young's interferometer. But the Young's interferometer case, we will have to move the double pinhole, moving around the make the recording all over the possible position. But it's not making things efficient. So how could we visualize just single shot all the coherence function? The trick is like this. This light is coming here. So you would like to see the coherence function of this field you are. They are guided into the Sanyak interferometer. This is beam splitter. One light is coming in and coming the clockwise, and the other one is counterclockwise, moving and put together. And we have a trick to put inside is a telescope, like to set up the Kepler type of telescope. That means one focal length is shorter, the other one is longer focal length. So when light passing from this way, the beam is expanded. When the light coming from this way, beam is shrink. So as a superposition together at the exit, they are mutually radially direction is shared. So the observation position at R is magnified by N, and the other one is demagnified 1 over N. So as a result, they have a sharing of the two positions. That is proportional to the radial direction. So we are able to observe directly coherence function in this field by making use of this kind of radial sharing interferometer. So here is some the specific the scheme we can make use of it. If you'd like to see the hologram is here. Hologram is created by physically or computer generated hologram, whichever you like. So hologram is placed lead out from this Heavy-neon laser, the special light modulator in this case, because this is computer-generated hologram. Or actual hologram could be also displayed here. And then it is imaged onto this ground glass. This is a rotating ground glass to completely destroy the coherence. This part is the generation of coherence hologram. Coherence hologram is generated on this plane. And now all the scattered field is now guided into this Sonic interferometer, which decode the coherence function and visualize according to the principle I briefly explained in the previous slide. And we will see the image on the CCD. So it looks like this. Here is the heavy-neon laser light is coming here. And here is the SL1 where hologram is located and it is guided. And so here is the rotating ground glass. The hologram is here, completely incoherent. The spatial coherence is destroyed. And they are guided into the sonic interferometer and it is detected from the image sensor like here. So this is a hologram. This is Dr. Naik's work. He was my former student from the India, Kochi in India. So he made this experiment with us. And so this is an object, and this is a reconstructed image of the phase and amplitude. The image is reconstructed as a contrast, and so contrast is detected to form in the displayed in the form of the image as shown here. So, what is the practical application of this coherence holography concept? You are familiar with the photogrammetry, that is the 3D shape measurement of the depth 3D shape, depth information. Often white light interferometer is used. And also optical coherence tomography of the sectioning, the depth direction. So in that case, the temporal coherence has been used. That is so far. That means broadband source. And we are going to do that, replace it with the spatial coherence by making use of the coherence hologram. What does it mean? So concept is as follows. The conventional technique make use of the broadband source, like supercontinuum. Some rich people make use of it, but practically most superluminescence diode with a point source, so that has a very high spatial coherence, but low temporal coherence. And so they make use of the actual time delay as a measurement. Now, in this case, this Fourier transform of this coherence function will be its source spectrum. So broadband source will give a high resolution. Instead, we have a monochromatic source, but we will have a spatially incoherent rotating ground glass in the extended source. This will give us the spatial coherence, short spatial coherence. And we can control the actual location of the spatial coherence. You can remember that by making use of this kind of source and changing this zone plate, we are able to scan the coherence between 2 points on the actual direction. By making use of this, we will be able to do the sectioning or the 3D object. So shown here is the interferometer. This is a gauge block 3D, the step heights, 400 micron step height. So usually people make use of the white light interferometer or such kind of device. Here we will use the laser, completely heavy-neon laser. That means very high temporal coherence, but destroys spatial coherence. And change the shape of the source by a spatial light modulator. This detects a DMD device, and changing the shape. This is the projected light source. Change the shape of the light source by modulating. We are able to scan the depth direction. Okay, again, thank you. Thank you for raising hand. Because I don't know how to handle the situation. I will try to ask the all after I finish my talk. So just moment, sorry for that. If this is not virtual, I would be very happy to have being interrupted. But sorry about that. But thank you for anyway letting me know that. Okay, so we will move this scanning on this direction, the coherence function. So shown here is the light source displayed on the, this is zone plate, but it may not look like it because it looks like this fire. But anyway, we will change the shape of the source. As you see, this is as you see, this is a special light modulator change the light source shape. Then the coherence function will move. And so there is the contrast, high contrast position will be changing as you see the contrast changing on the block gauge. So 400 micron steps. So it will mean that the coherence function is scanned like this way. So we are not just simply the polished surface, we are also able to measure such kind of scattering surface. So this is the Chinese coin, because this is the student from China performed this experiment. So we are controlling this to measure the 3D shape of this. We are controlling light source shape. As you see, zone plate is now changing the focusing. Focusing is not optical field, but it is the coherence of the actual coherence. What happened then is you see a lot of speckle here. Speckle, you see a lot of speckle. You will observe the change of the speckle as we change the light source. You will see here the contrast will changing, the speckle is blinking, and blinking's contrast will be changing from the bottom to top. And the highest contrast change position, we will be able to observe the shape of the object. So here is the such kind of measurement was taking place, making use of spatial the coherence. What is good for this is it is monochromatic. When the biological application, there is no the refractive index dispersion problem. It is monochromatic. Nevertheless, short coherence. It is a little bit different from temporal coherence application. So far, we have introduced the what is the coherence hologram is. Now I will move to the what is photon correlation holography. So again, we will make use of analogy. Here, this is the story of the history of the microson interferometer, which was created 1920. The microson created to position and light is taking in an interference. Basically, Young's fringes. Now, Humbly Brown and Twist and HPT intensity cross correlation. So instead of correlating the optical field, this first detect intensity, and intensity is correlated by numerical way and gets the image. This is called intensity correlation. So we have to have already idea about coherence holography. Why not go to the intensity interferometer? Of course, we can do that. This is a photon correlation holography where instead of the measuring this, we are detecting to the intensity and correlate inside the computer, and we will see the reconstruct the image. That is the scenario. That is really the analogy helps us to look at it. Now there are two more operations for the intensity correlation holography or photon correlation holography, where the scenario, first scenario is rotating around glass, and we have the hologram here deconstructed, and the intensity is taken, and also the correlation is taken by a computer. by through time averaging. This is one mode of operation. The other mode of operation is we stop the ground glass to rotate, and in such a way that it is stopped, so that what we see here is something like a speckle, because usually speckle is the changed and averaged out, but because this ground glass is stopped, so we will have a very clear the speckle, and we take two speckle, two plane of the record the speckle. And to get the depth information inside the object to reconstruct, we make this two plane and correlation through the correlation, spatial correlation instead of time correlation. So this is something like things like this. This is one plane we observed this speckle. This is the other plane some distance back, and we will take the correlation, take this and then we will take this one and make the spatial correlation in between. This correlation calculation will reveal what is recorded inside the hologram, like this way. This will reveal the object P is inside, and there is another object here. By changing the Z, we will see other object as well. So we have depth information is also the result. So experimental setup looks like this. This is the object and it is the hologram is displayed on the spatial light modulator. Again, the same way read out. And here is the ground glass. Ground glass is not rotating. This is static ground glass. And so we will have a lot of speckle in the far field. So we see this hologram. So we have this correlation, and through the correlation, this work was done with Dinesh Naik and Rakesh Singh. They are my former group member. They are not quite independent back in India. So final talk will be what is Holography. Holography is something we will see something hidden behind. So this guy is trying to see inside, but he cannot see what is inside because the light is scattered by here. So similar problem often happen in many cases. Transmissive diffusers. Biological tissue is the one the problem we encountered. Other is atmospheric turbulence we have disturbed. So how could we see something hidden behind this kind of the scattering media? That is one important issue. And similar issue of the reflection mode. This is not transmit reflective diffuser. So this is one of the MIT people are working. Is there is an object, someone standing here. There is a door here. The door surface is scattering wall, and so when you can see him inside, of course not, because of the scattering, you cannot directly see. But can we turn this scattering surface as if it were a mirror surface so that you can see it or not? This kind of address issue is often addressed, and not only by MIT, but the people in this is an example from the this is from this this is a rabbit. So this is a scattering surface. You cannot see it, but could we see some way? Of course, if the object is 2D, oh, sorry, if the object is 2D like this, then it's not difficult. If you have an image of the 2D object onto the ground glass, you can see it, of course, no problem. Like the movie screen scattering, you can see it because they are in focus. But now, when it comes to 3D object like this, so one position is now in focus, but the other point, other in the position is out of focus. So you cannot see it. So 3D is different problem. So our there's the solution are already known. One of them is using ballistic photons rejecting scattered light. So all many light, among that one is ballistic light. It is not scattered. So make use of this one and exclude all scattered light. The way to do that is one is give a short pulse and time gating so that only the direct the light that comes early will be selected, and the other one is very short coherence light so that only those interfere one each other will be selected, that is the scattered light is ejected like OCT. And this is one technique, but one problem might be most power and information of the scattered light are not made use of. They are wasted. All information is wasted. They have, of course, information, but they are not used. And energy, all energy is also not used. So another solution is time reversal, making use of phase conjugate mirror. One technique is 3D object is here, they illuminate by coherent light, the scattered light is coming here. And the scattered light is now recorded as a hologram, like here. And the hologram is reconstructed by lead out wave in the opposite direction. This is plane wave, and in such a way that the reconstructed light follows exactly the same path as in the reverse way, as if time reversed. This is holographic phase conjugation, so that this phase is cancelled, and then we get the image like this. And in this case, it is the critical alignment. This should be exactly the same location. And the image is formed in the object size, not here, outside. So this one is such kind of problem. And another way is like the adaptive optics. And people in astronomy takes the other approach. And very similarly, this is a ground glass. They have a random phase diffuser. And this is completely imaged onto here. So in this plane, you will put the spatial light modulator, phase modulation. So its phase is compensated as I phi, as this minus I phi, so that the phase is cancelled, so that we will be able to get the image like this. However, there is critical alignment, of course, but the most difficult thing is we don't know this what is this random phase. So one way is to get this image and iterative process until we get the clear image. So these are the technique already available. We take another different approach. This is what we call holographic correloscopy. And here is the ground glass. The key thing is we put a reference source as well. This is something like a guide star in the telescope people. The optics, they often use a guide star nearby. In this case, we have a reference source. And here, it is a kind of hologram. Real-time hologram is created on this ground glass. But ground glass diffuse the scatters light into here. So in the far field in here, we make the correlation, measure the coherence function here. And from that coherence function, we will be able to reconstruct this one. This is our scenario. And this is again the same type of sharing interpreter. And we call this holographic correloscopy. One mode of operation is field correlation, making use of interferometer. And the other one is intensity correlation. We have two modes of operation. So shown here is an example. We have an object ABC, and we have a reference source here, and hologram is created in real time. So from this side, we are standing. We cannot see anything here because of the rotating ground glass. completely destroys the waveform. Nonetheless, when all the scattered light guides into the sonic interferometer as I have described, so we will be able to see this object as a coherence function. Shown here is a similar experimental setup. Here is the object, and this is the reference, and it is guided here. Here is the rotating ground glass, where hologram is here, and the completely incoherent, spatially incoherent light is coming here, and this part is sonic interferometer, which reconstructs the hologram. Here is the low interferogram. Because, as I said, the image is reconstructed as a coherence function. So coherence function means fringe contrast. High contrast fringe means the field strength correspond to the image. So as you see, this part is the higher coherence. And we can detect this fringe contrast by fringe analysis. We are able to reconstruct this kind of image, like here. Again, another way of looking at here is the coherence holography is now optical field is hologram is here. And we make the correlation at the far field. And from field correlation, that means the coherence function, we get the image. Well, another way to look at it is the following. We are correlating, this is correlation of the optical field here. That means between here and here is far field. This is Fourier transform. Correlation of the Fourier transform is power spectrum of the optical field here. That is called Wiener-Hintgen theorem. So taking the correlation means Fourier transform of the power spectrum. Then it is equivalent to measure the power spectrum or intensity distribution immediately behind the diffuser. Will give us all the information about the object hidden behind the diffuser. So this idea can be explained as follows. Here we have, so far we have been taking the correlation, making use of the interferometer. Now we replace it just simply with a camera, high resolution camera, and we record the intensity distribution immediately behind the ground glass. Then we will have a hologram, and it is nothing but the digital hologram. We know how to reconstruct it. Just simply we numerically reconstruct the digital hologram. We will get the image. Very simple. So this is the experimental setup. We made this experiment in in Stuttgart. Dr. Singh is again from India. Another Singh, Alok Singh and Dinesh Naik. We are the team in Stuttgart at the time. So here is the object. Very close to the object, there is a fiber that sends a light as a reference, and this is a guide side. This is a rotating screen of the ground glass, so you cannot see this from this side because of the diffuser is here. And nevertheless, this is the screen immediately behind the diffuser. We still have hologram fringe contrast. So just what we have to do is just Fourier transform and reconstruct the hologram. As you see here, the object that is hidden behind the grating ground glass is we are able to see it. So much easier way of making use of the spectral intensity correlation is the following. We just simply no need of the rotating ground glass, but the ground glass is now static, and we don't need camera even. Don't need camera. Just we observe the speckle here, and the speckle correlation. This is covariance is calculated and gets the image. This is the simpler version. As you see, here is the object. Object is correlated. Correlation is here. The two image is shown. It is the magnified version is here. Here is we have an object. So thinking of the application to the biological application, we replaced the ground glass with the chicken breast, a 1.5 millimeter thick chicken breast tissue, and they are scattering, of course. And the object is H, the hologram H, and it is recorded like this is just speckle. We observe the speckle, and from the correlation of the speckle, we will be able to reconstruct the letter H that is the hologram object behind the chicken, hidden behind the chicken breast tissue. Oops, maybe time is out. Oh, no, sorry, I don't know what happened. Maybe something may have happened. Just I will go. You have to. Okay, just a moment. I stop the. I hope that we can come to that slide again. Okay, now, okay. So the final example is the how to make use of this characteristic. Here is the object here, and before, not this is not hologram, but different, but similar to hologram, but it is not exactly the hologram. Before taking hologram, the object and the reference point is illuminated at the same time, but instead we first illuminate point source, only one point source, and first record the speckle as the point spread function. This is a scatter. There is the speckle, and is there, and the object is here. So every point creates the the scattered field, its point spread function. In case this scatter is not very thick, this is shift invariant in such a way that it is kind of convolution. So we measure this first, this point spread function first, and then we illuminate all this area and take the second speckle and cross correlate each other. Because speckles are not correlated, their correlation length is almost speckle size is same as the diffraction limited. It depends on this aperture, numerical aperture size, so that we are able to reconstruct the object in the diffraction limited field. So this is the experiment is something like here. Here is the object, conventional microscope. You have a point source in a conventional microscope. You have a point source, clear point source. And you put the object, you will have a magnified object. Now, instead of this microscope object, we have a scattering layers, ground glass. So you have a point source, you have a speckle. You have an extended object illuminated by the coherent light, and it just creates a lot of speckle pattern. And now these speckles are mutually correlated. So this is the object is 6, and this is point spread function, and this is the object, this one. And cross correlated, from this cross correlation, we will get the object construct. And so we are able to have the magnified image, its function as a microscope. These are the Air Force pattern reconstructed. And also these are biological samples of the pine stem. So this shows, this one is the conventional microscope. This is this is scattering. Scattering the plate is function as the imaging device. So that is all I have to explain. So I like to summarize. As I said, the statistical optics and holography have been far away in the classroom, but they can get married, and then we will have some new technique, and where analogy, thinking of the analogy is very important. So I'd like to acknowledge this work has been done with many people with whom I work together. Dr. Wei Juan, he's my former PhD student, now established company in Japan. This is my associate professor, but now she's a professor at UEC. And Dr. Naik was my former PhD student, now IIT, IIST, space science in Trivandrum. And Professor Wolfgang Olsen and Dr. Pedrini is my, I was invited to join their group. And Dr. Pavel Pavlevsky is Czech Republic, and he was a postdoc in my group. And Professor Rosen was also, they worked together with in our laboratory for some times. And Dr. Alok Singh, now he was a PhD student at Stuttgart University when he came, when they worked together with him. And Dr. Rakesh Singh, he is now back in India now, and he was working with me in UEC as a postdoc in my group. And Dr. One, he is now teaching. He was also postdoc. He former my PhD student. He is now teaching at the Harvard University. All these people are very much important contribution to the work I introduced. Thank you very much. I hope I don't know. I stop here anyway. And do I better stop sharing? Okay. I hope that. Sorry that I have kept several people's. They need a question.
Thank you, sir.
Yes.
Now I was attending to a question regarding this topic. Then you can write this to the chat box.
Sorry that the voice condition is not very good, so I cannot comprehend what. Do you hear me well? Do you hear me well? Do you hear me well?
Thank you so much, sir, for
Yes.
this. Yes, sir.
Yes.
So we can take a couple of questions.
Okay. 5 minutes? Oh, what? Okay, I have this one. I take a. Okay, I'm ready to answer a question whenever you are ready.
So there is a question raised in question answer.
Yes. Do I see? Okay. Okay. Seminar chat. Do I have to see the seminar chat? Okay. How does a hologram differ from photograph? Okay. Hologram is the technique that is we make use of the coherent usually this is a very difficult problem. And conventional holography photography, you will see the picture, but it is just the intensity field intensity information is recorded, so you cannot change the viewing angle or the depth information. Nevertheless, if you have a technique to record optical field including phase and amplitude, the holography is such a technique making use of the laser interference, and the interference fringe location will have the information about the phase. Did I answer well, or someone could help me? Okay, may I move to the other question?
There are two questions in Q&A block.
Yes. Another question is, does SPL imaging can be enhanced with holography? SPL imaging. What does SPL image means? Stands for? I am not familiar. Eh? Sorry, I don't hear you. Well, SPL. What SPL?
So this is surface plasma resonance imaging. Surface plasma resonance imaging.
Sorry, the voice condition is very difficult to understand someone. So my question is
So
SP.
there is one more question,
Yes.
which is raised.
Yeah. Okay. Just a moment. How can I see it?
That next to participant window, there is a Q&A
Q&A.
tab.
Okay.
Q&A tab.
Okay. I got it. Okay. Is there any loss related to? I cannot see all. Just a moment. I cannot see all. How can I see all? Is there any loss related to holography and rest? I cannot see it. What? Sorry, that someone need help. Is there any loss related to holography rest? I cannot see it. I can see only holography. It is the question is much longer than this.
So I have unmuted the person who has raised this question. So I request Mr. Kamal Kishore Chore to ask.
Just a moment. Speaker does not work. Don't you hear me well? Do you hear me?
Yes,
Are you okay? Okay. So the question I found is there any loss related to holography? That is all. This loss is what loss? Information loss or energy loss? What loss? So I'll go to the second one because continuing. Energy, is there any loss related to holography or any error margin in holography technique? So here, at least the holography from point of view, the coherence function can be created. Nevertheless, the coherence degree of coherence will be lost. In that means highest coherence of the unity cannot contrast of the unity cannot be deconstructed. That is the conventional, like conventional holography, the zeroth order, and the first, second, the plus, minus, first, and the plus first and minus first energy is split into that order. So in this way, energy will be only part of the energy is used in the conventional holography. Similarly, the coherence will not be as high as unity. Did I answer?
Thank you. Yeah. Thank you, sir, for your answer.
Yeah.
Hello. Thank you, sir, for your answer. My first question was: is there any? Yeah, sir. Is there any loss related to holography? That much.
Yes. Yes.
In terms of energy or in terms of information, both. is there any losses related to some to this topic, technology holography?
Final part, is that any related to the conventional holography? What did you say?
No, no. Is there any loss related to holography in terms of both energy or information?
Basically, it is if you know the conventional the holography, the same as that holography, because the coherence holography and the conventional holography, they obey exactly the same wave equation and the same formula, so that the information loss or the such every loss which you may think of is the same loss. For example, information loss of the resolution loss in conventional holography is the numerical aperture of that hologram. Similarly, the coherence, the strongest coherence, that can be also depends on the numerical aperture it subtends the hologram. In that sense, it is what you can think of is the almost applied to this special hologram. Did I answer your question?
Yes, sir. Yes, sir. Thank you very much, sir.
Thank you very
Thank you
much.
very much, sir, for the answer.
Okay.
Okay.
Yes, I find another one. What would be the effect of recording an hologram of object using two different? I see. The question is what happens if usually hologram will be recorded with one reference beam, but instead of using one reference beam, what happens is we have two difference beams. Oh, that is interesting question. Well, there is two ways. If we add extra another one reference beam, and then we will be able to interpret as another object. And so one of the two difference is the really difference, and the other difference is part of object difference. That way of interpretation, then you will see other the reference light will be reconstructed when you illuminate by one of the reference beam. But if you put, your question is that if you put the illuminate the two reference beam, and when recontrasting, you are also using the same two beam, then the object will be reconstructed as the just like you use the single beam. Did I answer? I hope that I hope that I'm understanding your question well. So did I answer all the questions that has been
Yes,
raised?
sir.
I'm not sure if I could answer as well. I'm sorry about that.
Yes, sir. So
Yes.
thank you so much, sir, for the
Yes.
precious time you have spent for the webinar for our chapter.
Yes.
On the behalf of OSS Student Chapter MNIT Jaipur, I really thank you very much. And after this pandemic is over, we really want to see you in person in our university. Right?
Okay. Thank you very much for the kind the invitation. It is really the bad time of all over the world, and I hope that the things becomes much improved in the shortly. I myself is now, because of the COVID, I'm not in the campus. We are off from the campus, and I hope that we will have another in future good opportunity to see in person somewhere in the world, maybe in India. Thank you very much.
Thank you, sir. Thank you.
Thank you. I will go out. Thank you very much.
Okay. Thank you, sir. So I also thank all the participants to participate in this webinar, and we will shortly mail you a feedback link, and you can fill that link to get your certificate, that e-certificate of this webinar. So we will be mailing we will mailing this feedback link in a couple of minutes. Thank you.